Hello. Yesterday we were discussing Green's function, and today we are going to continue with the discussion on Green function. And yesterday we did one thing. There we ended our lecture, and at the end of the lecture we were discussing how to solve a boundary value problem, an inhomogeneous boundary value problem, via you can say Green's function method, and not only the construction of you can say Green's function was important. We were also discussing as to how one can find the solution for it. Okay, how can one find the solution part? So this is what we were doing yesterday. Let us understand. Okay, so let us understand. So up today we are going to start with, again I'm just going to briefly write solution of boundary value problem via Green's function. Okay, and till yesterday, what I was doing was, while we solve a boundary value problem. So let us say my boundary value problem is inhomogeneous case given by L by x is equals to f of x. So what I would do, I would not consider this problem, rather I would consider this problem. That is, we consider the homogeneous case. And given these boundary conditions, as if so all of these are boundary conditions. All of these are boundary condition. Now, if I find a Green's function, if I construct a Green's function for this homogeneous case, let's say my Green's function is gx comma zeta, then my y of x is given by, then y of x is given by integral a to b, like wherever your this interval of existence is there, as if wherever your boundary value conditions demand you to be in between. So let's say if these initial bound, if these this differential equation is defined for all x belongs to a comma b, then y of x is given by integral gx comma zeta, and then you have this f of zeta, and then you have d of zeta. Okay, this is how you find the solution for this. Your f is what? Your f is this inhomogeneous part, or sometimes referred to as driving function, or you can say your what should I say? Driving function, forcing function, probably inhomogeneous function, you can say. Or you can say non-homogeneous part. So all of these things we have discussed till now, and this is how you find the solution for the boundary value problem. And yesterday we were doing, yesterday we ended our lecture here. So now today we are going to do a few problems regarding this particular theorem. Let us start with the problem. Now, let us solve a differential equation, or you can say a boundary value problem. Via Green's function. So let us solve a boundary value problem via Green function. And what is that boundary value problem? Boundary value problem is given by d2 y upon dx2. And then you have plus y. You have a negative written all over here. And you have equals to x. Is that clear? And given boundary conditions, y0 is equals to y pi by 2 is equals to 0. Okay, so given is that y0 is equal to y pi by 2 is equal to 0. How to solve this particular boundary value? How to solve this particular boundary value problem? Let us understand. Okay. Is the screen visible or not? I hope I was doing something. Is the screen visible? No. कुछ बोल नहीं रहा है?
No,
नहीं
not
है?
visible.
ओके ओके ओके, सॉरी, सो सॉरी। फर्स्ट मीन्स ओके, 2 मिनट दो मुझे।
Now it's visible.
It's visible right now. Okay. So see, what I was doing was yesterday I was doing some solution of boundary value problem using Green's function. So what is a boundary value problem for those who have joined today? So boundary value problem is a problem where you have a differential equation aided by some boundary conditions. Now these boundary conditions usually are given on the function itself. Those differential equations at times are referred to as IVP, initial value problem. And differential equations where your boundary value problem are on the derivatives as well. So on the derivatives also, if you have some initial conditions given, such problems are called as boundary value problem. And we have already discussed that Green's function is one of those methodologies by which we can find the solutions of these boundary value problems. Obviously, there are other methods also, but sometimes you will find that Green's function happens to be a very right choice while solving these differential equations. Okay, so what is this L? L is, you can say, L is your linear differential operator. L is your linear differential operator. This is your linear differential operator. So if it operates on, let's say, y of x, and you get your f of x here. So this particular differential equations are called as inhomogeneous differential equation or non-homogeneous differential equation, which is our like main focus right now for physics people. Whoever are doing physics, mostly you'll find that you have condition, you have function, you have differential equations of inhomogeneous kind, which we are going to solve. Let's say equations of Helmholtz kind, Gaussian expression, that is Poisson equation. All these equations are, after all, inhomogeneous differential equations whose solutions can be extracted by the usage of your Green's function. Okay, so how should I find the solution for this? So what I would do, I would not consider this particular differential equation. That is, I'll not consider the inhomogeneous differential equation. Rather, I will consider only the homogeneous part. Okay. So if I solve this homogeneous part, and for this homogeneous part, I will construct a Green's function. So I will construct a Green's function here. And once my Green's function is constructed, so construct a Green's function for your homogeneous part. And once your Green's function is constructed, your function yx is given by integral a to b gx comma zeta f zeta d zeta. Your f is your forcing function, which happens to be on the right, or your non-homogeneous part, or you can say your forcing function. Okay, so all of these things are possible. Okay, so now let us solve a problem via Green's function. Okay, and those who have not taken the lectures before, kindly take those lectures. Otherwise, things will be difficult for you. Although I'll keep on revising things up. Don't worry. So overall, what I am supposed to do first? This is an inhomogeneous differential equation. You can see on the right hand side there's a function of x. So what I'll do, I will try to construct a Green's function for the homogeneous part. So I'll try to construct a Green's function for the homogeneous part. Now, if I find this Green's function for the homogeneous part, what I will get, what I should get, I will have to solve this particular differential equation, that is d2y upon dx2 plus y equals to 0, which gives me the solution as a cosine of x plus b sine of x. This is quite clear to you. Like these are the solutions for the differential equation d2y upon dx2 plus y equal to 0. And given the boundary condition y0 equal to 0, it implies what? It implies your a has to be 0. Isn't it? If if y0 is equal to 0, it implies your a is 0. And if your y pi by 2 is 0, then it implies what? It implies your b is 0. So if a is 0 and b is 0, it implies yx should be trivially 0. So yesterday we were discussing that if the differential equation when solved, given with additionally supplied with these boundary condition, if all of them together form a trivial solution, then for such differential equations or for such boundary value problem, there is a sure existence of Green's function. If you remember, yesterday I gave you a theorem which suggested that if at all your differential equation when solved, aided with these boundary conditions, if the solution that comes out is a trivial solution, then Green's theorem is unique and it surely exists. So Green's theorem definitely exists. Green's function definitely exists. The Green's function definitely exists, and it exists uniquely. Okay. Now, what are the conditions for finding the Green's function? So first, I told you that Green's function would always satisfy the differential equation. So Green's function would always satisfy this differential equation given by this. It implies what? It implies that your gx comma zeta, and I told you whenever you are going to write this differential Green's function, you're going to separate it into two parts. That is, first part is this. Here I can write a cosine x plus b sine of x, and then I can write x lying from zeta to pi by 2. And here I can write, let's say, c cosine of x plus d sine of x. If I'm not wrong, I think this is right. Okay. Now, overall, you can understand that this is your Green's function. Now, the second property that Green's function holds is that it also satisfies the initial boundary condition satisfied by the differential equation. So, differential equation, the solution of the differential equation suggested that y0 should be 0. It implies your g0 zeta should be 0. And g0 zeta being 0 implies what? It implies your a will be 0. That you can clearly see. And your g pi by 2 comma zeta, because here your conditions are from 0 to pi by 2. Like these conditions are given on 0 and pi by 2. So what I will do on the farther end, that is at pi by 2, you can expect that your d is 0. Because you see, if you place pi by 2 here, cos pi by 2 is already 0, sin pi by 2 is 1, and overall if it's 0, it implies your d has to be 0. So like your Green's function now gets modified, and it's you can express your Green function as this in this form. And today we're going to do some Gauss law also. So first lecture probably is on Green's function. The second lecture I'll take on Gauss law, so that बहुत दिन हो गया electrostatics नहीं किया है. So like this is d sine of x, and I think there it should be d0 ना, तो c cosine, sorry. Is that clear? Now, third condition that Green function satisfies is that your Green's function is continuous throughout. You can see that sine x is a continuous function. You can see your cosine x is a continuous function. So on this half interval, your sine x, this particular function is continuous. On this half interval, c cosine x is continuous. There is no issue about it. The only lack of continuity there that may exist is on the zeta point. So at zeta point, there is a possibility that your Green's function may be discontinuous. So what I can do, I can simply use this continuity condition. That is, my Green's function must be continuous at zeta. And if it is continuous at zeta, it implies your b sine zeta is equal to c cosine zeta. So b sine zeta would be equal to c cosine zeta. And fourth condition that I told you was that the derivative of this Green's function is discontinuous at zeta. So derivative of this Green's function, this first order derivative of this Green's function suffers a discontinuity or jump discontinuity at zeta, and that jump discontinuity is given by minus 1 upon p naught zeta, where p naught is the coefficient of the highest order derivative. So highest order derivative happens to be, if I consider my original problem, if I take minus here, then it will be minus 1. And if I place my minus here, then it will be 1. So let's say if this is my initial condition, so I'll go accordingly. So I'll just take it as minus, that is 1. Okay. 1. Okay. So overall, I understand all of these are my, you can say, initial conditions. These are conditions which are necessary, or you can say the conditions which conditions on Green's function. Like Green's function has following condition: one, that it satisfies the differential equation; second, that it satisfies the initial boundary condition specified in the differential equation itself. Then you should have the Green's function to be continuous. And lastly, your Green's function, the first order derivative, suffers a discontinuity, and the quantum of the discontinuity happens to be minus 1 upon p naught zeta. And p naught is the coefficient of d, like the highest order derivative. So here, highest order derivative, minus 1 is here. You can as well place minus here, and you can take 1 also. So it's entirely up to you. Okay, overall, I'll use this condition. So what it will yield me? It will yield me that minus sine of zeta minus b cosine zeta is is 1. Is that clear? This is condition number 1. And then you have this condition number 2 here. So you can use these two conditions. You can find what would be b. So if I want to find what is my b, so if b sine zeta is c cosine zeta, what I can do, I can simply take b as c cosine zeta divided by sine zeta. These expressions are quite weird. I cannot help it. So it is minus c sine zeta minus c cos square zeta divided by sine zeta is equals to 1. And overall, I could write, I can write it as minus c upon sine zeta is equals to 1 implies c is equal to minus sine zeta. So I found that my c is minus sine zeta. And if my c is minus sine zeta, that implies your b would be equals to minus cosine zeta. If I'm not wrong anywhere, if you just see, this is fine. And overall, I would write that my g x comma zeta, that is my Green's function, to the boundary value problem, I have constructed as minus cosine zeta sine x for all x lying between zeta and 0. And for all x lying between zeta and pi by 2, this is, I think, minus sine zeta. And then you have this cosine of x. Is that clear? So this is your Green's function. So this is what we have constructed, our Green's function. Like, is that clear to you? Now, in order to obtain your yx, what I would do, yx is equals to integral 0 to pi by 2. Instead of a and b, now you have 0 and pi by 2. And then you have this function x written all over. Also, you have g x comma zeta. And understand f of x is equal to x. And understand that in order to find y of x, what I have to do, I have to simply integrate my f zeta with g x comma zeta with respect to zeta. Don't forget, yesterday we were forgetting this stuff. So it is like zeta here. And then you have this d zeta. Okay. So what I would do, now I will see here on the left hand side, you see your expression is a function of x. Okay. And g x comma zeta is a function of both x and zeta. Is that clear? So what I would do, I would probably try to break my limits from 0 to x and then from x to pi by 2. Why I would do so? Because see, these pi by 2 and 0, all these will ultimately end up giving me a constant answer. Like see, whatever integrates, if you place 0 there and if you place pi by 2 there, overall it will become 0. It will become some constant. However, the higher limits and this lower limit would give me some function of x, and which indeed is the case, because here you have this y of x. So what I would do, here I would integrate like zeta, and now here you are in a clue. Here you are clueless what to write. See, in this case, understand my point, that in this case, if I see that my zeta, because these limits are on zeta, so zeta varies from x 0 to x. Is that clear? So if I integrate it with respect to zeta, it implies what? These are the limits for zeta. It implies your zeta lies between 0 and x. If your zeta lies between 0 and x, it implies your zeta is less than x. And if at all your zeta is less than x, then this is the definition that needs to be followed. See, zeta is less than equal to x. So I will simply write minus here. I will write sine zeta, and then I will write cosine x. Is that clear? भरत को क्लियर है, अल्पना को क्लियर है?
यस सर।
है ना, दो बच्चों ने
भैया।
ज्वाइन किया, वो सुन रहे हैं, तो वो लोग क्लियर है नहीं है? मतलब obviously you will not get what I'm doing because you have not taken the initial lectures on this क्या कह सकते Green's function, but if at all you will take those lectures, I've already uploaded them up, then you will be able to get things. So if this is the case, here you can see that your zeta is greater than x and zeta is less than pi by 2. Implies here I will write that my zeta in any case is greater than equal to x and less than pi by 2. So if zeta is greater than equal to x, it implies I'm in this regime. If I'm in this regime, so it would be like minus will come here. Zeta would be accompanied because your function is f of x, and then you have cosine zeta, and then you have sine of x, and then you have d of zeta. So your integration will go over zeta. So cosine x you can take as a common out. So I'll take cosine x common out here, and just try to find this integration. So this integration would be, I believe, this thing minus cosine zeta. So I'll write minus cosine zeta. Then what I would do, minus integral of the derivative of zeta is 1. Sine zeta integral is minus cos zeta. This will be plus, and cos zeta integral is plus sine zeta. So this will be it. Kindly see if there is some difference in your answer also. So if at all I'm making some kind of mistake. So here you have this zeta, cos zeta. So zeta remains there. Cos zeta integral is sine zeta. And then you have negative zeta's derivative is 1. Cos zeta's integral is sine zeta. And sine zeta again integrated to give you cosine zeta. And this is from x to pi by 2. Is that clear? I don't think there is an issue till now. If at all you find some issue, please let me know, because once we have done wrong, then it will be completely wrong. So this is like minus cosine zeta. You just start placing x here. So this is minus cosine x, and then you have this sine of x. And while you place 0 here, so it will be all 0, so forget about it. Minus sine x, you just try to place pi by 2 here. So pi by 2, cos pi by 2 is 0. Sine pi by 2 is 1. And this pi by 2 remains intact. And minus x sine of x and minus cosine of x. Is that clear? I don't think there is an issue till now. So overall, if I just try to integrate entire stuff all, so this will be like minus cosine x sine of x, and this will be minus minus plus, so forget about it. I think what remains is x cosine square x plus x sine square x, and then there should be some minus pi by 2 sine of x. So overall, your function y of x must be equals to what? So your y of x must be equals to what? X minus pi upon 2 sine of x. Is that clear to you? So this is how you can find the solutions for the function itself. So here we were doing in the previous 4 lectures, we have seen how to construct a Green's function. In this lecture, we have seen how to find the solution of the bounded value problem using the Green's function. Is that clear? Is that clear?
Yes, sir.
So let me let me give you some motivation from physics. At least you will be understanding what I want to suggest. So if I want to write Gauss law, what is my Gauss law? Gauss law suggests that if my electric field is not a induced electric field, okay, is a conservative vector field, that is one which is born out of, you can say, static charges. So one which is born out of static charges. We know that this particular electric field, which is born out of the static charges in electrostatics, the divergence of that electric field is given by rho upon epsilon. Is that clear? So for example, if I have let's say this is my arbitrary volume, this is my arbitrary volume, and a charge, and I want to write, because of this arbitrary volume, I want to write my potential at this particular point. Okay, let me write the potential at this particular point. And let's say this is my origin from where things are being referred. Okay, now if this is the origin, and let's say this distance is given by, and what I will do, I will use primed coordinates for my charges and unprimed coordinates for space. I will use unprimed coordinates for space and primed coordinates for my charges. Is that clear? So if I just write that this is your r vector dash and this is your r vector. So the point where I want to find my electric field, let's say this is your point P, it is distant at r from origin. Okay, is that clear? So overall, I know that this distance would be, I think this would be, if I write r vector in this fashion, this will be, I think I should write it as r vector minus r vector dash. Is that clear? So this is it. Now, if I want to write the potential due to this entire arbitrary volume at point P, what would be the strategy? The strategy would be to write volume as to write the potential as K dq upon whatever is the distance. This is your r square, and you have to integrate it. Okay, you have to integrate. So all these, let's say these charges, dq dash charges, whatever small dq dash charges are here, what I would do, I would integrate all these dq dash charges, and I'll integrate all these dv potentials that are generated through these dq charges and integrate them up. So if I have to, like, if there are, like, this is dq dash, another dq dash would be here, another dq dash would be here. So summing all these up, like integrating all these up, would give me the total potential due to this arbitrary volume nu dash at point P. Is that clear to you? This is something that you know from a standard 12. If you don't know, let me know, so I'll help you out. So you know that for a point charge, the formula is K Q upon R. So instead of point charge, you have an in principle point charge only here, that is dq. So because of this dq, you know, and for other all dqs you will be able to know, and then you have to just integrate it up, and you will get this particular potential at point P. Is that clear?
Yes, sir.
Okay. Let's say this particular dq dash is distributed in the volume d tau dash, and let's say this entire density of this the charge density is uniformly distributed, and the volume charge density is given by rho. So I'll write rho r dash. So instead of writing dq dash, what I would write, I would simply write it as 1 over 4 pi epsilon naught. And then I would do one thing. I would simply write it as rho r dash d tau dash divided by r square. And this r square I can as well write. And you should understand that three symbols I'm using. See, here I'm using this kind of symbol, and here I'm using these kinds of symbols. I'm at a lack of the, like, I do not have much symbols left with me. So this is what I'm doing, because R naught and all those stuff, that becomes all the more confusing. So I'm using this kind of thing. Okay. So now if I just write it as R vector minus R vector dash ka mod ka whole square, then I think it is, sorry, my mistake. Electric field nahi hai, potential. So potential takes k dq dash upon R. Na? Electric field में R square होता है, potential में you have R. Is that clear? ठीक है, ये हो गया. Now you already know that if your del dot E vector is rho upon epsilon naught, and if this electric field is born out of static conditions, that is the static charge condition, you know that your electric field is a conservative vector field. Why I'm time and again explaining you, because you people have done MSc, and you know that it is not always possible. It is not always true that your electric field is a conservative vector field. It is only true that electric field is a conservative vector field provided it is born out of charges at rest. So if you have charges in motion, let's say if you are talking about something called as induced electric field, then this electric field is a vortex field. It is a non-conservative field. So there you will find that del cross E vector is null, not null. Here you can say that your del cross E vector is a null because it is electric. This electric field is a conservative vector field. Okay. So it implies if electric field is a conservative vector field, that implies your del cross E must be 0. And instantly I'm reminded of a theorem which suggests that curl of a gradient is 0. So what I do, I say that my electric field can be expressed as a gradient of some potential function, and this v is called as potential function. Negative is written in order to justify the direction. In order to justify the direction, I put a negative. So this is minus grad v. Is that clear? So if I replace all these up, so I know that del dot E vector is equal to rho upon epsilon naught, and this will give you, I think this particular thing would give you, this particular thing when placed here would give you del square v is equal to minus rho upon epsilon naught, and this is sometimes referred to in text as Poisson equation. Okay, so we know that this is a Poisson equation, and I'm writing it all over here. So this is a Poisson equation. Del square v is equal to minus rho upon epsilon naught. Okay, is that clear? And this minus rho upon epsilon naught, and this particular differential equation is a second order linear differential equation, isn't it? So this is a Laplacian equation. Poisson equation is said, but I always consider this like this is Laplacian now. So this is d square v upon dx square plus d square v upon dy square, you can say, or whichever coordinates you want to write in. This is a second order linear differential equation. So this is a second order differential equation that I'm discussing, and it is equals to minus rho upon epsilon naught, and minus rho upon epsilon naught, and this is an inhomogeneous case, kind of inhomogeneous case only. And here you can find that this here your function is there. There's a function on the right hand side, and this function is your forcing function, or you can say your non-homogeneous case, non-homogeneous part. So basically, you can treat this particular differential equation as an inhomogeneous differential equation. So this inhomogeneous differential equation, when solved, gives you this answer. That is, v is equal to integral 1 upon 4 pi epsilon naught rho r dash d tau dash divided by r vector minus r vector dash. I hope till now everything is clear. Now I'll do certain manipulation. I already know that if I want to solve my differential equation, if I want to solve my second order inhomogeneous differential equation, my y as a function of x, and here my y as a function of r, but you can say my v as a function of r, my v as a function of r is not this r is given by integration instead of this fx, I will write minus rho r dash upon epsilon naught. And since I have written minus rho r dash upon epsilon naught, what I would do, I would simply rho r dash, and then there should be a Green's function. I think now there will be problem with people. Are you getting my point, or are you not getting my point? You see, what I want to suggest is, I want to find the potential at this particular point. And I want to find the potential at, again, there is a mistake. I want to find the potential at this particular point, that is point P. And del square V is equals to minus rho upon epsilon naught is something that I know. That is, this is from the Gauss law. This is from the Gauss law. I know that this is true. The solution of this differential equation would give you V. And already I know that V can be written as 1 upon 4 pi epsilon naught. And then I can write it as rho r dash d tau dash upon r vector minus r vector dash ka whole mod. Is that clear? Now, but also I know that this is an inhomogeneous case. What I can do, I can simply write it in this fashion also. So if I just compare these two up, so let me just compare these two up. So let's say this is my equation number 1, and let's say this is my equation number 2. I will try to modify the definition 1. And what is the definition number 1? So I'll do what? I'll do something like this. So I will simply write it as 1 upon 4 pi epsilon naught. And instead of this rho r dash, I will multiply this rho r dash with minus, divided by plus epsilon naught, and again multiply with plus epsilon naught. And then I have this r vector minus r vector dash modulus, and then I have d tau dash. Again, just try to put this inside. So this will go inside. What it will form? Minus rho r dash upon epsilon naught. I'm just modifying my equation number 1. So I'm just modifying my equation number 1. So if I modify my equation number 1, what I would get? I would simply get it as 1 upon 4 pi r vector minus r vector dash ka modulus d tau dash. This is your potential function as r. Now you just compare these two up, and you can find that your Green's function for Poisson equation happens to be 1 upon 4 pi, and a negative sign also, sorry, because you have multiplied negative here, so here also there will be negative. Because ultimately you have positive. So overall this will be minus 1 upon 4 pi, and then you have modulus r vector minus r vector. Is that clear?
सर
हाँ बेटा बोलो.
सर जो सोल्यूशन फाइनल सोल्यूशन लिखते हैं ग्रीन फंक्शन मल्टीप्लाई करके, वो हम उस जीटा पॉइंट पे लिखते हैं ना, जहाँ पे फंक्शन डिसकंटिन्यूअस रहता है.
हाँ
बट यहाँ पे हमने सर वॉल्यूम एलिमेंट लिया हुआ है डी टाउ डैश, क्योंकि
ठीक.
3 डायमेंशन में ये फंक्शन, इसलिए.
हाँ, ये 3 डायमेंशन में, इसलिए here you have 3 dimensions. So instead of r dash, you'll write d tau dash, or simply you can write it as d3 r vector dash, because now you are considering volume integral instead of line integral. Like instead of single integral, now you have this volume integration.
ओके सर.
Is that clear?
यस सर.
है ना? So again, because physics में you'll have all these. Physics में you are going to encounter something called as non-relativistic scattering problem. Also, there you have to solve this that's Helmholtz differential equation, del square k square psi is equal to something. So again, there also we'll invoke Green's function approach. So I'll go along, and I was just wanted to give you this particular thing because we are doing Gauss law now on the other end. That is why I wanted to tell you. Is that clear to you?
यस सर.
उसको अपना समझ में नहीं है.
हाँ भैया.
ठीक है. So this is your Gauss law. This is what we were discussing. So I hope to meet you in the next lecture, and there we'll do electrostatics. This was what I did yesterday, but somehow things were not going right, so I all over repeated. Tomorrow we are going to continue with Green's function. Today we are going to do Gauss law, at least something new somewhere. Okay. Or meanwhile, I'll give you a problem so that at least you do something. So just find me using Green's function only. Chalo ye kar lo, simple. d2y upon dx2, and you have a negative sign. Again you have minus y, and then it is equals to x, given y0 is equal to 0 and y1 is equal to also 0. Let us solve this differential equation. Tomorrow we are going to do something called as Bronsky approach. So that also is important, and at times you'll find that most questions are done using that. And then there is another approach of expanding your function into series of some orthogonal functions. So that is also another approach. So there are 2 or 3 approaches in order to construct a Green's function.
सर इस अब प्रॉब्लम में हम ग्रीन फंक्शन डिराइव भी कर सकते हैं.
इस पर्टिकुलर प्रॉब्लम के लिए ग्रीन्स फंक्शन डिराइव कर सकते हैं, ऐसा पूछो.
जी
हाँ, हम कर सकते हैं. प्रॉब्लम जब इलेक्ट्रोस्टैटिक्स करेंगे तब करेंगे, बिकॉज हियर जस्ट आई वांट टू गिव यू एन इनसाइट. मतलब यहाँ मैं तुम्हें सिर्फ इनसाइट देना चाह रहा हूँ कि देखो ग्रीन्स फंक्शन कैसे रिट्रीव किया जाता है.
यस सर।
है ना? We'll do all
ओके
these
सर।
things in detail.
ओके सर।
Okay. So try to do this problem फटाफट से, so that क्या करना है? Approach is simple. First thing is try to find the solution for the homogeneous case. If I find the solution for homogeneous case, y of x will give you some a e की power, I think x plus b e की power minus x. Isn't it? यही होगा.
यस सर।
हाँ चलेगा सर. हाँ. Now if you find y0 is equal to 0, it will give you, I think, a plus b equal to 0, and y1 is equal to 0, it will give you a e plus b e की power minus 1 equal to 0. From here you can see that if a is equal to minus b, if you replace minus here, so you know that your b is equal to 0 from here, and if b is equal to 0, then a is 0. So overall you know that yx equal to 0 trivially is the only solution. And if there is a trivial solution to this thing, then I know that I can construct something called as your Green's function. So Green's function exists, and it exists uniquely. So this is what I taught you yesterday. That is the existence of Green's function, theorem on existence of Green's function. Now, in order to find my gx comma zeta, I'll find gx comma zeta. Rest I'll leave it to you. So if I just find my Green's function, what would be my Green's function? So my Green function would be, I will try to solve this particular, because Green's function would satisfy this differential equation. So if Green's function satisfies this differential equation, like how would I find this differential equation, homogeneous part of this differential equation? If my Green's function satisfies, then my Green's function gx comma zeta can be written as a e की power x plus b e की power minus x for all x lying between zeta and 0, and for all x lying between zeta and 1, it will be like c e की power x plus d e की power minus x. I hope it is clear. And if you just try to impose some condition, that is, if you just try to impose conditions, the in condition number 1, that is your your g0 comma zeta should be 0, and that implies your your a plus b has to be 0. And similarly, if you apply, I'm just going to write all these things. Second condition that I'm going to apply, c e की power 1 plus d e की power minus 1 should be equal to 0. Another condition is this. Then I'm also going to use the condition g zeta plus comma zeta should be equal to g zeta minus comma zeta. That is the continuity condition. And the fourth condition that I'm going to use is gx at zeta plus comma zeta minus gx zeta minus comma zeta should be equal to minus 1 upon minus 1, that is 4. So if you use all these four conditions, you are going to find your Green's function. This is a hint I'm giving to you, and I'm writing this Green's function so that if you are doing it, at least you do it right. So your Green's function you will find v equals to sine hyperbolic x sine hyperbolic zeta minus 1 divided by sine hyperbolic 1. Your x lies between zeta and 0. And if your x lies between zeta and 1, this answer is sine hyperbolic zeta. And then you have the sine hyperbolic x minus 1 divided by sine hyperbolic 1. So this is what you are going to get. Like you just put all these conditions together and you will get this Green's function. And once you are done with this Green's function, the solution of y of x you will find to be equivalent to, I think this would be some, you just try to find, this is sine hyperbolic x upon sine hyperbolic 1, and then you will get. So this is what you are going to get. So just try to integrate all this stuff up. I'm not going to do it for you. I have given you the answer. I've given you the conditions that you're going to follow. ये सारी conditions follow करो. Find this Green's function, and with this particular Green's function, try to integrate this particular thing from 0 to 1, and this will be f zeta into gx comma zeta d zeta. You just integrate this stuff up, and you'll get this y. I hope you'll get
सर
it.
-1/1 कैसे लिखा है एक बार बताना।
हाँ बेटा,
तो -1/1 कैसे लिखा आपने वो डेरिवेटिव वाली कंडीशन ग्रीन्स फंक्शन के ऊपर।
-1/-1 वो ऐसे लिखा, जो कंडीशंस इसका जो कोफिशिएंट है वो देखो, या तो तुम एक काम करो, इस पूरे माइनस को उठा के यहाँ ले जाओ, कोई दिक्कत ही नहीं है, तब आएगा -1/1। पर अगर इस माइनस को यहाँ इंस्टेट यहीं रखते हो, देन इट विल बी -1/-1, बिकॉज याद करो ये
ये
होता
आगे।
क्या था। हाँ बेटा बोलो।
हाँ जी, नहीं बताइए सर एक बार, वो
हाँ
आगे माइनस दिया हुआ था क्या क्वेश्चन में।
आगे माइनस दे रखा है।
ओके ओके, ठीक
अगर
है
इसको
सर।
हटाना चाहो तो इसको उठा के यहाँ लगा दो, तब इंटीग्रेट करते समय यहाँ माइनस आ जाएगा।
यस सर, ठीक है सर, ठीक है,
तो
ठीक
कोई
है
फर्क
सर।
नहीं पड़ने वाला उससे। ठीक है, आई होप इट इज क्लियर। ये तुम कर लेना,
यस
दिस
सर।
इज समथिंग आई हैव लेफ्ट टू यू, लेफ्ट इट टू यू फॉर एज अ होमवर्क। नाउ वी आर गोइंग टू डू गॉस गॉस फॉर अनदर सेक्शन। ओके।
Okay.